Hello and welcome back. Today we're going to talk about simplifying radicals. What's a radical? Well, I'm glad you asked. A radical is an expression with a square root. Looks like this. So this whole thing is called a radical. The little thing on the top is called the radical symbol, and whatever's underneath it is called the radicand. Now, there are rules for radical expressions. The first rule is no perfect squares hiding under the radical symbol. So here's the radical symbol, and you can't have any perfect squares hiding under there. Rule number 2, no fractions in the radicand. So underneath the radical symbol, no fractions. And rule number 3, no radicals in the denominator of a fraction. Radicals on the bottom, very bad. So let's look at each rule and see what it means. Number 1, no perfect squares hiding under the radical. Now, first thing we need to do is talk about what perfect squares are. I always like to make myself a table, and on the left is x, and on the right is all of those x's squared. So 2 times 2 is 4, 3 times 3 is 9, and so on. So if we look at the square root of 25, well, that's made by 5 times 5. So the square root of 25 is just 5. Okay, what about the square root of 50? Well, that's not on my list anywhere, but I know that that's 2 25s. So see that 25 under there? That's a hiding perfect square. I need to pull that out. And when I pull it out, it becomes the square root. So 5 times the square root of 2. How about the square root of 108? Well, that breaks down into 36 times 3. 36 is a perfect square that's hiding underneath there. I need to pull that 36 out. When it comes out, it becomes 6, and I have 6 times the square root of 3. Now, what happens if you get a number that's like really big? And you don't know, you can't just see what perfect squares are hiding under there. I usually just start with some big perfect squares and see if they divide in evenly. So 486 divided by 144, yeah, it doesn't work. Divided by 121, nope, that doesn't work either. Divided by 100, nope. 486 divided by 81, yes. 81 times 6 is 486. Now I see that this perfect square is hiding in there. I'll take the 81 out. It becomes a 9, and I get 9 times the square root of 6. Now, this also applies to variables. So, x times x is x squared. X squared is a perfect square. So, square root of that is just x. It gets more complicated, though. Look at this one. The square root of x to the 6th times y. Now, here's a hint for you. Variables with even exponents are perfect squares, okay? So if I break this guy up into x to the 6th times y, x to the 6th, that's a perfect square. And when I pull it out, it becomes x to the 3rd times y. The exponent is half of the even exponent. So 3 is half of 6. Let's try another one. So the square root of 25 x to the 5th y to the 7th. I need to find perfect squares that are hiding in there. Well, 25 is a perfect square. And then I'm going to take that x to the 5th and break it up into an even exponent and an odd. So x to the 4th times x. Same with y. That y to the 7th, I can take y to the 6th times y. Now I can pull out each of these perfect squares. 25, x to the 4th, x to the 6th, and I get 5 x squared y to the 3rd times the square root of xy. So that's how rule number 1 works. Let's talk about rule number 2. No fractions in the radicand. Again, we'll pull up our table of perfect squares. And our first example is the square root of 9 over 25. Can't have that. But we can break it up into the square root of 9 divided by the square root of 25. Well, the square root of 9 is 3, and the square root of 25 is 5. How about the square root of 121 over 36? Square root of 121 divided by the square root of 36 is 11 over 6. We're going to do more with that in just a minute. But right now we need to work on rule number 3. No radicals in the denominator of a fraction. Again, we'll pull up our table of perfect squares just as a reference. And let's say we have 2 over the square root of 5. Yeah, you can't have the square root of 5 on the bottom. So what we're going to do is what we call rationalizing the denominator. And we can multiply the top and bottom of the fraction by the radical we don't want in the bottom. So we'll multiply the top and the bottom by the square root of 5. And if you look just at the bottom here, square root of 5 times the square root of 5, is just 5. And then the top is 2 times the square root of 5. And we can leave it like that. Let's try another one. 4 over 5 times the square root of 3. We can't have the square root of 3, so we multiply the top and the bottom by the square root of 3. So square root of 3 times the square root of 3 is 3. So now on the bottom we have 5 times 3, and on the top we have 4 times the square root of 3. So we have 4 times the square root of 3 divided by 15. One more. 4 divided by 3 times the square root of 2. Again, the square root of 2 can't be there, so we'll multiply the top and the bottom by the square root of 2. Square root of 2 times the square root of 2 is 2, so the bottom is 3 times 2. And the top is 4 times the square root of 2. So we have 4 times the square root of 3 over 6. Now be careful. See that 4 over 6? We need to always reduce the fraction if possible. And 4 over 6 reduces to 2 over 3. So this reduces to 2 root 3 over 3. So if we take each of the rules separately, that's what they look like. But we need to put it all together. All right, buckle your seatbelts. Again, we're going to start with pulling up our table as a reference. And if we've got something that looks like this, yikes, 288 over 147 under a radical sign. Okay, so we need to break that up, 288 over 147. And find any perfect squares that are hiding underneath those radicals. So 288 is 144 times 2. 147 is 49 times 3. We'll pull those perfect squares out. We get 12 root 2 over 7 root 3. Uh-oh. We can't have a root 3 on the bottom. So let's come down here where we have a little bit more room. And we'll multiply the top and the bottom by the square root of 3. Again, that's called radicalizing the denominator. So on the bottom we have 7 times 3, and on the top we have 12 root 6. So we have 12 root 6 over 21. Can we reduce this? Yes, we can, and that reduces to 4 root 6 over 7. One more. Let's try it with some variables. So we get the square root of 10x to the third divided by 27y to the 8th. Whew. Break it up into top and the bottom. Okay, then we can look for any perfect squares. So 10x to the third, we can break that into 10 times x squared times x. No perfect squares hiding inside of 10. And then 27 is 9 times 3. Y to the 8 is already an even exponent, so we can just leave that. And we will pull out our perfect squares. So we get x times the square root of 10x divided by 3y to the 4th times root 3. Again, we cannot leave that root 3 on the bottom. So we'll come down here, get some more room, radicalize the denominator, multiply the top and the bottom by root 3. And if you look at the top, there's 2 things under the radical. We'll just multiply those 2 together. So x times the square root of 30x divided by 9 times y to the 4th. Wow, there's a lot going on with all those rules, but break it down, rule number 1, rule number 2, rule number 3, and then put it all together. Thanks for being here.